Okay, guys, so this is the last section. Oh, it just went away. Last section of chapter 10. Oh, it went all the way back there. Section 6. It kind of takes us in a completely different path than what we've been seeing. We've been doing basically shapes and what kind of forces then are holding those shapes together. And this is going to talk about matter and the changes of state. So changes of state being solid, liquid, gas. And then we're seeing how these are held together. Now, you see these little water molecules? Since it's H2O, we know that all the forces holding all these little guys together, are hydrogen bonds. All right, so we do know that, some of these forces that are holding it together. Now, we're going to look at like how do you break these forces to get some of these states of change. All right, so because depending on the energy that you're applying, are these forces like stronger or are they weaker? Because if you have solid ice, that's a stronger bond than gas molecules to say. So melting and freezing, a substance, so melting and freezing are kind of this, not necessarily the same thing, but they're happening close to the same temperature is what I mean to say. Melting is when you're going from, right, a solid to a liquid, right? Where you're melting ice, that ice cube is turning into a liquid. If you're freezing something though, I'm taking that liquid and I'm putting it in the freezer and it's going from a liquid to a solid. This is all happening at the freezing point. Now we're always degrees Celsius in here. So this is happening at 0 degrees Celsius. All right. Calculation using heat effusion. So we want to know what the big takeaway from this is. How much energy? How much energy do I need to freeze maybe a sip of water versus a full cup, right? It's that little bitty amount of water is going to freeze before that whole cup does. So how much energy is it going to take to do that? So this is how we do it. Scientists have figured out the amount of heat released when 1 gram of liquid freezes at its freezing point is the amount of heat needed to melt 1 gram of solid. So for water at 0 degrees, this is 334 joules. Now joules is the measurement of energy. So solid to liquid, liquid to solid. At 0 degrees, it's going to take 334 joules. Now I will have, we won't write that down quite yet. Kids will know this here in a second. All right, so calculations using heat effusion. This is how you do this then. The heat to freeze or melt, we know is 334. So that's 1 gram. Well, what if I have 15 grams of ice? Well, if I have 15 grams of ice, this is going to take us back to those cookie days when we were doing conversions. 1 gram of ice needs 334 joules. Now, I need to put grams of ice down here because that is division and it's going to cancel out. So my answer is going to be left in joules, and that's what I'm looking for. How much energy, how many joules am I going to need to do this? So if it's on top, you multiply. 15 grams, well, that's canceled out. 15 times 334 is 5,010 joules. All right, so it's all about what do they give you, and they're always usually going to give you grams, so then your grams go on bottom with your joules going on top. That's almost always what they do. All right, that is not wanting to erase. There, now well. Okay, so let's look at this learning check then. So how many joules are needed to melt 5 grams of ice at 0 degrees Celsius? And this is going to be really important that we know 0 degrees Celsius, because here later on in the PowerPoint, we're going to get different temperatures, and depending on that temperature depends on what number we use. So since it's at 0 degrees, I'm going to say, okay, 5 grams. I know that 1 gram takes, what was it, 334? So then you're going to take 5 times 334. Let me get my calculator out here. Or I may have left my, is it here? I think I left my calculator at home, guys. I did. Okay, so I'm going to have to use my phone here. Bear with me. So I'm going to take 334 times 5, and that is 1,670 joules, right? Those grams have canceled out through division. I know you guys are probably super excited to see we're back into conversions. We will continue to get back into those, so maybe get used to them. On B, it says how many joules are released when 25 grams of water at 0 degrees freezes. Once again, you can see where we're melting, we're freezing, but the big thing is that we are at 0 degrees Celsius. So 25 grams, I know that 1 gram is 334 joules. So that is going to be 25 times 334, and that is 8,350 joules of energy to get 25 grams. And I'll measure some of these out in class so they can see exactly how much water this is. And we'll give them an idea of like, okay, well, how much energy do we think that will be? All right, so here's the solution. They're showing you what I just did. All right, now we have something called sublimation. And this occurs when particles absorb heat to change directly from solid to gas, so they skip that liquid phase. Dry ice can do this. It sublimes at negative 78 degrees Celsius. Frost-free refrigerators do this. When we prepare freeze-dried foods, we do this. So it just skips that liquid phase. It goes straight from solid to gas. And if you guys have ever seen, nitrogen gas or liquid nitrogen, you can see you get like this, it looks like a big block of ice, and you can't touch it, like do not touch it, but it almost looks like it's giving off a fog. And there is no liquid, it's going straight from like this block of ice straight to gas. All right, let's look at evaporation and condensation. So think about that. When you have condensation, I always think of a cup sitting there on a hot summer day, and it gets wet on the outside. All right, that is condensation. Another example of condensation is if you're in the shower and you're taking a very hot bath, you get out and the windows are all, or the mirrors all fogged up. That's condensation. Evaporation also happening. So when that mirror that is all fogged up, when it finally cools down in that bathroom, it evaporates because it's not there anymore. It's not like your window or your mirror's all wet. It evaporates. So that's the two different types here. So let's go down to boiling. At boiling, all the water molecules have enough energy to form a gas, so bubbles appear. So when you are boiling water, it's like there's enough energy that heats it up and you form this gas bubble, and that bubble is then what comes up to the top and what you see. All right, so let's look at heat of vaporization. So this is going from liquid to gas, right? We just saw where we went from liquid to solid. We're looking at liquid to gas now, and there's a different number. Think about that. How is it the same? Is it going to be the same energy to freeze water versus to get it evaporate? It's not going to be. It's different. Different things are happening. So when you're trying to get it to go from a liquid to a gas, like you're separating those particles out even more. It's going to take a little bit more energy to do that. And that's why we have to heat it up to do this, to get that energy. And this, once again, this 2,260 joules, that is to get 1 gram of water to evaporate, or 1 gram to turn back into a liquid, to condense. All right, so let's look at that. 2,260, that's the new number we're using. And remember, water is doing this at 100 degrees Celsius. All right, so if you look at this, here's heat of vaporization. So if you look, water is right here. And this is what we're going to deal mostly with is water, so we'll be using that 334 number. We'll also be using that 2,260 number. Now that's a polar covalent. Yes, it's H2O. It has a hydrogen bond. It's hydrogen force, but it's still polar. Like, it's still covalent. Hydrogen bonds are still sharing. If you look at ionic, ionic is the strongest bond. I told you guys that in the previous sections. So look at the number you use for ionic on each of these. Whereas you can see gases, think of a gas. Or if I have like ethyl alcohol sitting out here, if you get some on your hand gets cold. It's because it evaporates so quickly. It doesn't take much energy to get that to happen. So you can see like even propane, look at that, only 18 joules versus water at 334. So yeah, it evaporates quickly, and when it evaporates, it usually leaves your hand feeling a little bit cold. So that's what's going on here. All right, but once again, everything we're doing right now is dealing with water, so that magic number of 334, when you are going from, at 0 degrees Celsius, and when you're at 100 degrees Celsius, that 2,260. All right, so here's a learning check. Right away, I'm like at 100 degrees Celsius, so we're going to be using this number. And I know that's for 1 gram, but here it says how many kilojoules are released when 50 grams. So I have 50 grams, I'm gonna write down what they give me, and I'm like, okay, well, 1 gram is 2,260 joules. If 1 gram is 2,260, how much is 50? Well, I'm gonna multiply, right? And it's on top, so I can see that I'm gonna multiply anyway. So let's take 50 times 2,260, and that is 113,000 joules. Now you can see where they asked for kilojoules. Kilo means 1,000. So there's going to be we're going to move this 3 spots to make that 113. So the answer is 113 kilojoules. All right. So here's the summary of the changes. We have, at 0 degrees Celsius, you're freezing. You're also melting when you're right at 0 degrees. And remember, there's that weird area this is happening at 0 degrees. What happens if you're 1 degree? 1 degree is technically you're no longer melting or freezing, or what if you're -1? So we're talking right at 0, you get this kind of in-between phase. We think of it at 32 degrees Celsius, or 32 degrees Fahrenheit for us, or not 30, yeah, 32. And sometimes at 32, I'm like, it's raining. I see rain. It's 32, it's freezing, yet there's rain. There's no ice, there's no snow. Or vice versa. We've had snow when it's like 33 or 34 degrees out, and it all depends on that atmosphere. But here at 100 degrees, we're getting this, it's evaporating or it's condensing. We're going to look at what happens if you're like in between 0 and 100. What if you're at 50 degrees Celsius? Then what's happening? There's not as much energy needed to be used there. All right, so this is what we're doing, a heating curve, because we know, what if I have ice, where we just recently had a lot of ice? What if the ice melts and then it also then evaporates? What if it goes through all of those phase changes? How much energy did it take all that ice outside to melt and then evaporate? Because that's what happened to most of it, right? So this heating curve shows us what's going on. We have sloped lines to show an increase in temperatures. So if you look, this right here, my melting point, this is 0 degrees. This right here is 100 degrees. So right here, I am ice. I am a solid. Right here, I'm in that in-between phase. I'm either going into a liquid or I'm becoming a solid. I'm kind of in between. And then here, I'm a liquid. This is 0 all the way up to 100. So I'm liquid, and then here's at 100, I mean that liquid, some of that liquid's turning to gas, and then eventually 100 and above is all gas. Now you've evaporated. All right, so how much energy does that take? Well, I'm going to look at each individual spot. Like this takes so much energy to cross over. This takes so much energy when you're a liquid and you're just heating up, but you're still a liquid. And then once you're a liquid and you want to cross over to a gas, that takes so much energy. So we're going to add all these steps up. Now, if you are a solid, like you're clearly a solid, you're ice, you are ice cube, this will also take a step. We're going to look at all of these. These different lines, whether they are flat or angled, diagonal, it's going to tell us how to solve this. All right, so here's a learning check. A flat line on a heating curve represents, so we're talking, when I say flat line, I'm talking this right here, all right? That is a temperature change, a constant temperature, a change of state. Well, it is a constant temperature, right? That is 0 degrees or 100 degrees. All right, and if you look here, it is constant temperature, but you are also changing a state. You're also crossing over into some new state of matter at that point. B, a sloped line on the heating curve represents a temperature change, right? That your temperature's increasing or decreasing. It's not a constant temperature, but it's not a change of state, so it's just number 1. Now a cooling curve is much like this heating curve. You see my heating curve though, I'm increasing 0, I'm increasing to 100, like I'm getting hotter. That's why it's called a heating curve. A cooling curve is the exact opposite, but it's still doing the same thing. And when we do the math will still be the same. So I start out as steam, I'm getting colder, oh, I turn into liquid, colder, 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 and ice. All right, so we're cooling things down. And we're using those sloped lines to indicate that this temperature is decreasing. The plateaus, of course, are telling me that I'm getting a change of state here. So the learning check, when I'm looking at it, water condenses at a temperature up. Now remember, condensation is when it goes from gas to liquid. When it does that is at 100 degrees Celsius. At a temperature of 0 degrees Celsius, liquid water is going to, at 0, we're assuming it's going to freeze. At 40 degrees Celsius, water is a liquid, right? Anywhere between 0 and 100, the 1 to 99, that's going to be liquid water. When water freezes, heat is, well, think about this. If it's freezing, heat was removed, right? And that is what is showing here. If you're freezing something, you're not heating it up. Now, if I want it to evaporate, I'm going to heat it up, right? Think about heating up water. It evaporates. All right, so heat calculations. That's what we're going to look at next. So we did a few heat calculations a second ago at just 0 degrees and at just 100 degrees. But like I said, that is very rare. Like normally there's some kind of temperature increase or decrease. So it says to reduce a fever, an infant is packed in 250 grams of ice. If the ice at 0 degrees Celsius, so right here, at 0, there's my ice, melts and warms to body temperature, so it's heating up, how many joules are removed? So basically, how much energy did it take to do this? So what I'm going to have to do is I'm going to do a math problem for this. And that magic number was 334, so I'm going to take 250 grams. And I know that for 1 gram, it takes 334 joules of energy. And let's see what that is. Let's get that number first before I move on. Pull my calculator up again. Okay, so 250 times 334. So this is 83,500. Now for this line, I'll do a different color. This line right here, you are going to take the specific heat of water, okay, which is, well, first, you're going to take your mass times your specific heat of water, and we're always dealing in water. If I gave you anything other than water, I would give you the specific heat, but for us, it's always going to be 4.184. That's how much, that's, you know, each thing has a different, like water is going to be trickier, like if you're warming up milk versus water versus an alcohol, like they're all going to have these different numbers, specific heats. And then by the temperature change, because we need to know, well, how much did the temperature go up? Did it go all the way up to 100 or did it stop at a certain area? Well, we see that it stopped at 37. So when I do this, my mass is 250 times 4.184. That is a constant. That will always, if we're dealing with water, that 4.184 is always going to be there. And it went up 37 degrees, 0 to 37. So I'm going to take 250 times 4.184 times my 37, and that is 38,702. So now I've got these two numbers. I am going to add them. All right, add them together. So I'm going to add that 83,500 to that 38,702, and that gives me 122,202 joules. Now you'll see them say kilojoules a lot, so you could say, hey, that's 122 kilojoules, or 122.2 kilojoules, however you want to say that. So that is what you're doing. So what I will have the kids do in here on their periodic tables, I'm going to have them draw one of these curves, and I'm going to have them write 334 times mass. I'm going to have them write 2,260 times mass, because that's what you're doing here at 0, that's what you're doing at 100. Here I'm going to have them write mass times 4.184 times, a delta T means change of temperature. I'm going to have them write that down on their periodic table so that they will always have that. It'll be a quick place. They always have their periodic tables on them in here. Quickly pull that out and be able to get that and do any of these problems. All right, so if you want to write that down somewhere safe, like that you can get it out right away, do that. All right. So they're doing what I just did, 122,200 joules. So let's look at this learning check. When a volcano erupts, 175 grams of steam at 100 degrees Celsius is released. So I'm going to do a plateau. There's my 100. How many kilojoules are lost when the steam condenses, freezes, and cools to -5? Ooh, so I'm at 100. I go down to 0 and then go down to -5. So I've got 4 steps involved here. I've got 1, 2 plateaus, and I've got 1, 2 diagonals. Anytime you have a diagonal, you're going to use that mass, specific heat, and the temperature change. So on this one, I'm going to do 2,260 times 175. Here, I'm going to do my mass, 175 times 4.184. And my temperature change is 100. I went from 100 to 0. Now when I'm at 0, I'm going to take my mass times 334. And here I'm going to take 175, my mass, times my specific heat, times my temperature change. It went to -5, so it went from 0 to -5, 5. Now I'm going to do all these calculations. 2,260 times 175. That is 395,500. 175 times 4.184 times 100 is 73,220. 175 times 334 is 58,450. And then lastly, I have 175 times 4.184 times 5. Even though it's a -5, the temperature change is 5. So that's 3,661. Now you are going to add all of these numbers up. So I'm going to add all of them up. And I got 530,831. Now my rounding may have been off a little bit, but if I'm looking up here, this is joules. My kilojoules is going to be 530 kilojoules. So my rounding's off a little bit. It's going to be 529. They rounded all these numbers where I didn't. All right, so you can see their solution here. How they had 396, 73.2. So they rounded. They rounded a little bit differently than I did. But that's how you would do one that actually starts out like 100 and goes all the way down and is freezing and goes beyond freezing. Now I could have some that was a gas and be like, it was at 102 degrees and went all the way to -5. Well, then that would give me 5 steps that I would have to do. We are going to have some worksheets on this, so let me know if there's anything you're not understanding. The worksheets are mostly just dealing with this math and maybe making sure you understand the difference between your melting, freezing, evaporation, condensation. So anyways, yeah, if there's anything at all that you guys need, let me know, and have a great day.